Hello gentlemen, welcome to our video on 15.6 practice. Here we're just going to take some opportunities to look at problems and go through the solving process. So number 39 says a mixture of 0.2000 moles of carbon dioxide, 0.1000 moles of hydrogen gas, and 0.1600 moles of water vapor is placed in a 2.000 liter vessel. The following equilibrium is established at 500 Kelvin. We have carbon dioxide reacting with hydrogen gas in equilibrium with carbon monoxide and water vapor. So A says calculate the initial partial pressures of carbon dioxide, H2, and H2O. So to do that, we have to use Pivnert. That's how you find a partial pressure of a gas. So the first one we'll look at is carbon dioxide. So the partial pressure of CO2 is going to be nRT over V. So it's 0.2000 moles. I don't need to write that. We get it. Times the temperature. And I'm going to put 3 sig figs in my temperature there just to make this more of a valid problem. Okay, and when we simplify for pressure of CO2, we get 4.10 atmospheres. Okay, so that's the first pressure. The other we'll do for H2. Same equation, nRT over V. Moles of H2, we have 0.1000 moles times R times T. And we'll get, for this one, was it 2.05? Okay, and lastly, for H2O, same equation, nRT over V. H2O is 0.1600 moles times R and your pressure of H2O is 3.28 atmospheres. Okay, that's how you would do part A. Now part B is at equilibrium. The pressure of water vapor is 3.51 atmospheres. Calculate the equilibrium partial pressures of carbon dioxide, H2, and CO. Okay, so we need an ice chart for this. So if my equation, which is all gaseous substances, is like so, then you make an ice chart. Now we know our initial pressures. We just found them. For carbon dioxide, it was 4.10. For hydrogen gas, it was 2.05. Water vapor, it was 3.28. We weren't given any information on carbon monoxide, so it's 0. We're told in the problem, part B, that at equilibrium, water vapor is 3.15 in terms of its pressure. That's an increase by 0.23 atmospheres. So since they're all in a stoichiometric relationship of 1 to 1, here in blue, they're all 1 to 1, that means the change is going to be the same for all of them. So this is going to increase by 0.23. It's going to increase because these are both products. The products will increase. If one increases, the other has to increase. And here my reactants are going to be decreasing since the products were increasing. And since they're all in a 1-to-1 ratio, they will all decrease by that ratio. Giving me 1.82 atmospheres here and 3.87 atmospheres there. So B says, calculate the equilibrium partial pressures. Here they are. We have done so. C says, calculate K sub P for the reaction. Well, K sub P can be found by using your equilibrium constant expression, where you have your concentration. In this case, it's not concentration. It is just your pressures. So you have your pressure of CO times your pressure of H2O over your pressure of CO2 times your pressure of H2. These are all partial pressures. Now we plug them in. So at equilibrium, 0.23 times 3.51 over 3.87 times 1.82. When we do this, we get 0.11 as our Kp. And this is letter C. Letter D is asking us to find K sub C now for the reaction. Well, K sub C and K sub P are related. In this way. So delta N is our change in moles from our balanced chemical equation. Up here we have 1 mole of each product, so that's 2 moles total. We have 1 mole of each reactant, that's 2 moles total. So we say the difference, we're taking the difference of gaseous products and reactants. These are all gaseous substances, so that's going to be 2 minus 2 for delta N. We do have K sub P, so let's substitute that in. We're looking for K sub C. R is 0.08206 atmospheres, liters. T is 500 Kelvin. Raised to a power of delta N, which is products, 2 total, minus 2 of your total reactants, 2 moles. And 2 minus 2 is 0. Anything to a 0 power, which is what this is raised to 0 power, is going to be 1. So this all reduces to 1. So you have 1 times your K sub C, which is just K sub C. K sub C equals 0.11. Okay, so that's 39. 45 here gets into our video on applications of the equilibrium constant, looking at reaction quotients. So I'll just do part A here. For part A, it says at 100 degrees Celsius, the equilibrium constant for the reaction, phosgene in equilibrium with carbon monoxide and chlorine gas, has the value K sub C equals 2.19 times 10 to the negative 10th. Are the following mixtures of phosgene, carbon monoxide, and chlorine gas at 100 degrees Celsius at equilibrium? If not, indicate the direction that the reaction must proceed to achieve equilibrium. Okay, so for A, we're looking at 3 concentrations. And we want to plug these in to our reaction quotient to see if they equal K, which K is your constant at equilibrium. So we're looking to see if Q equals K. If not, then we're not at equilibrium. If it does, then we are at equilibrium. So we're dealing with concentration, so we use Q sub C here. It's going to be my products, my concentration of products, over my concentration of my reactant. So now we plug in. Carbon monoxide is 3.3 times 10 to negative 6. Cl2 is 6.62 times 10 to negative 6. And phosgene is 2.00 times 10 to negative 3. That's going to give me 1.1 times 10 to the negative 8th. So for this particular problem, if my K sub C was 2.19 times 10 to the negative 10th, and I just found my Q sub C, which is 1.1 times 10 to the negative 8th, they are not equal. My Q sub C is larger. Since my Q sub C is larger, I'm going to need to get it down. This value has to come down to this value to achieve equilibrium. So basically, the reactions going right now, we're not at equilibrium, and we're trying to see which direction the reaction is going to proceed as it reaches equilibrium, because it will. It's either going to proceed to increase your concentration of your reactants or proceed to increase the concentration of your products. So it's either going to go left or right to achieve equilibrium. So you have to see which way it's going to go based on this value versus this value. Okay, we want this 10 to the negative 8th to go down to 10 to the negative 10th. So if we look at our fraction, in order to get this value to equal this one, to go down, my denominator must increase and my numerator must decrease. So in terms of the balanced chemical equation, that means your reactants must increase and your products must decrease. In terms of forward and reverse reaction, that means that your products are going to collide together. As they collide together, they're going to use themselves up, which means they're going to decrease, and they're going to be forming more COCl2, which of course means that it's going to increase the concentration of COCl2. So the reaction will proceed to the left, favoring phosgene, which is COCl2, and increasing its concentration as it reaches equilibrium. So that is how you would analyze A, B, and C. I'm only going to do A here because B and C are just other examples of the same thing.